All right, I think I'm going to get started. Participants' number seems to be leveling off, and everyone can always go back and watch it online if they missed the beginning. And there's a lot to cover. Okay, so welcome to Working with Asynchrony Generically. My name is Niebler. I work at NVIDIA. Recently started working at NVIDIA. I came from Facebook. So I've been really interested the past few years in all things asynchronous and how best to express asynchrony and how we might be able to extend the standard, particularly the standard library, to give it a coherent model for asynchrony. Okay. This talk is in two parts. This is part one. I highly encourage everyone in part one to attend part two. And for the people that are going to be in part two that aren't in part one, they're missing out because I don't think part two is going to make a lot of sense without this one. So we're going to start by talking about the goals. Oh, I forgot something. Before I really get into this, I want to say that if you have a question at any point during the session, go ahead and type it into the Q&A window. I'm not going to be paying attention to the chat or to the raised hands. So just type it in to the QA. We'll get to questions at the end. Go ahead and write the slide number down if it's a question about a particular slide. And you could also find me in GatherTown. I'm not going to be in GatherTown after this session because I'm going to be jumping right into another session. So find me after session 2. I'll be in GatherTown then. That's track E. Thanks. Okay, we're going to be talking about the goals. What is the executor's proposal? Why has the committee been doing this? We're going to talk about some simple examples. I'm going to introduce you to these things that we call senders. I'll talk about the life cycle of an asynchronous operation in the sender-receiver model. We'll go under the hood and we'll look at how a concurrent operation actually executes. We'll implement a simple algorithm. And then we'll talk about how this work intersects with C++20 coroutines, which I know a lot of people are very interested in. And part 2, we'll talk about structured concurrency, cancellation, and then we'll work through an extended example, code example. And it looks like we've got a lot covered in part 1 and not much in part 2, but it's actually quite the opposite. All right, the goals. My vision for executors, and the vision of my team, the people we've been working with, my co-authors, is that we'd like to provide the standard library with an asynchronous analog of the STL. With the STL, we got containers, iterators, and algorithms. Algorithms that were generic over like any sort of data structure, and it's a brilliant piece of work. But sequence algorithms, which is what the STL deals with, is really only one very narrow domain. And so we'd like to basically do what Stepanov did for the STL, but for asynchronous algorithms. So what we're going to do is we're going to provide a full suite of standard asynchronous algorithms based on real-world requirements. So there'll be algorithms like then for chaining work and when all for launching work, a bunch of work concurrently, sync wait for blocking for it, repeat, stop when, timeout. Not all of those algorithms are actually in the proposal yet, but that's the plan, that's the vision. We'll propose a standard set of abstractions, otherwise known as concepts, that we derive from the algorithms themselves. We want to be able to efficiently interoperate with coroutines, because I firmly believe that coroutines, the sync await style, is how people are going to want to write their asynchronous programs in the future. And then an open and extensible way to specify where, how, and when work should happen, which execution context. In In the long run, we hope to provide some ones like in the standard out of the box, like an event loop, portable access to the system execution context. That might be in the Windows thread pool or Grand Central Dispatch on Mac OS. And we'd like to provide a nursery for spawned work. And I'll talk a little bit about what I mean by that. Okay, so what is the proposal? The proposal is numbered P2300. If you are familiar with how the committee operates, we put out these P-numbered papers. And the name of the paper is called STD-EXECUTION, and it proposes a set of concepts. First and foremost, concepts that represent a handle to a compute resource, which we call a scheduler, a unit of lazy async works, which we call a sender, and a completion handler, or a callback, if you will, and we call that a receiver. Now, a note about the name senders and receivers. What is being sent from the sender to the receiver is the result of an asynchronous computation. That might be a bunch of values if the asynchronous computation completes successfully, or it might be an error, or it might even be a cancellation signal, like this work was stopped early. Okay. We're going to be proposing, P2300 proposes a small initial set of generic algorithms. It's a very small fundamental set of algorithms at this point, just minimal support at this point. Then when all sync wait, a bunch of really interesting algorithms whose names start with let. And then utilities for integration with C++20 coroutines, which like I've said, is I think essential. Okay. So let's get right into some code and see what working with the STD-EXECUTION might look like in the future. Okay, so here is a really simple example for launching concurrent work. And I think, this is ultimately what most people want to be able to do, right? They want to be able to, say, launch a bunch of work on a particular scheduler. In this case, it's a thread pool. And then change some work to be done after it's, picked up by that thread pool, some compute intensive work. Do these 3 tasks concurrently by executing them in a when all. And then wait for it all to finish and extract the results. Okay. Now what P2300 actually proposes is this namespace. This concept. This is syntax, C++20 syntax for declaring a constrained local variable. It's just like auto, except the compiler checks that it conforms to the scheduler concept. The sender concept, when all then, and schedule algorithms, and the sync wait algorithm. Those are all in the paper. And just like ranges, we support pipe syntax, so you can make your code read left to right. If you like, it's optional. You don't have to use that. And I want to point out a really interesting fact about the design. From here, everything in this red box is done with 0 allocations, which I think is pretty remarkable. You can schedule work, asynchronous work on an execution context. You can execute it concurrently. You can block for it to finish. All with 0 allocations guaranteed. I'll mention a little bit why the design makes this possible. Okay, let's look a little bit more closely at this example. What is actually happening here is that you are building a tree of your work. And when I said earlier that senders are units of lazy asynchronous work, when you execute this line of code, nothing actually happens. You just build a tree, and it remembers all the different nodes in this tree. But it's not a tree like like a red-black tree or some runtime data structure, everything here is stored statically in member variables. So there's no allocations creating this tree. You could think of it as an expression template if you're familiar with that term. Okay. Now, what in here is a sender? Well, there's a lot in here that's senders, actually. So, for instance, the schedule algorithm returns a sender. The then algorithm accepts a sender and returns a sender. So these three expressions are also senders. When all operates on senders and returns a sender. So the design is self-similar in this way. So it makes it really easy to compose complicated expressions out of smaller, simpler ones. Okay, we'll look at a second example here. You definitely want to be able to transition from one execution context to another. So let's take a quick peek at what that looks like in P2300. So in this case, we have two pools of threads. We're going to be accepting requests, and then we're going to be processing them. And processing these requests might take some time. So we don't want to be holding up, our I/O threads, which have high latency, with a bunch of compute. Right. So here we have this function that's going to accept and process a bunch of requests. Right. The first thing we do is we use the on algorithm from P2300 to specify where work should happen. So on our low latency scheduler, accept your request. And notice that accept request here is a function that returns a sender. So it returns a unit, a lazy unit, a unit of lazy asynchronous work. Then we're going to transfer onto a different execution context, onto our worker thread. Then we're going to chain some work onto that. We're going to process the request, and this is going to happen on the worker threads. And now I'm going to use an algorithm that's not in P2300, but it's provided by the libunifex library to do everything in a loop and repeat. Okay. Now, I'll point out here that this is probably not how you would actually implement it. This is only going to fetch the next request after the previous one has finished processing, which is, that's not ideal. It could make sense if you launch many concurrent instances of this accept and process requests function. You could also write it as a coroutine. So notice that we have changed the return type here to be a task. This is a task type that's defined in the libunifex library. Unfortunately, we don't have a standard task yet. We're getting there. And then in an infinite loop, or a loop that appears to be infinite, I'll talk about that in a bit. We call the on algorithm. We specify where this work should happen, where we accept requests, and then we co-await that. Now, on returns senders, but senders are awaitable in coroutines. So then we get the result of that request here. And then we co-await on again to transition to execute this work on this execution context. So the TLDR here is that schedulers produce senders. Generic async algorithms accept and return senders. And that makes the design self-similar. So if these are some of the algorithms that we're proposing in P2300, I'm not going to go through all of these. But look, here is sender, and this is kind of like the pseudo signature of it. You can see it takes a sender and returns a sender. And all of these take senders and return senders. Right. That's the really important point here that I want to make. It makes it possible to build complex things out of simple things. Now I'd like to talk about the control flow of sender-receiver. I understand I haven't talked at all yet about what a sender is or how any of this actually works. So let's peek a little bit under the cover is what's going on. So everything starts with a scheduler, so you can specify where the work happens. If you don't specify a scheduler, it's just going to happen in line, and that's not very interesting. The scheduler has a single function on it. It's called schedule. You call schedule, and you get back a sender. Sender, like it's, it's a, again, you're going to get tired of hearing me say this. It's a unit of lazy work. This is a bit of empty work. It's not going to do anything, but it's going to start in the context of that scheduler. So if the scheduler is a handle to a thread pool, then when this sender starts, it's going to start on a thread in that thread pool. So anything you chain onto that sender will be in that execution context. And if you're just using the algorithms, that's really all you need to know about sender-receiver, about P2300, because all of the everything else, all the other parts of the design, that's all for implementers of algorithms. So some of us are going to want to implement algorithms. So let's talk a little bit about what happens inside the box. So there's a receiver. Receivers are callbacks or completion handlers. There's a function that connects a sender to a receiver, and you get back an operation state. This is all of the state for that asynchronous operation that needs to be kept alive for the duration of that asynchronous operation. Okay. It has one function on it. It's called start. And start is what actually makes the work execute. What is happening here is that it is being enqueued for execution. Things aren't enqueued for execution until start is called. So if at this point you've connected a sender to a receiver, you've gotten back an operation state, you could drop the operation state on the floor and no work has happened whatsoever. It's fine. Okay, so you call start on this thing and time passes and eventually the operation completes. And after the operation completes, it notifies the receiver that his work is done. And this is the control flow of sender-receiver. In this box, these are all implementation details of some algorithm, an algorithm like then. Right? So then is going to implement a receiver. And it's going to implement an operation state. What does a receiver look like? I mentioned earlier that asynchronous operations can complete in one of three different ways: successfully, with an error, or with cancellation. So receiver has three different functions on it: set value for success, set error for the errors, and set done for cancellation. And when the operation state notifies the receiver, what happens is that it calls exactly one of these functions exactly once. That's all you really need to know about sender-receiver. We start with these two concepts, scheduler and sender. They're very simple. They each have one function. We have this receiver concept. It has three functions. And we have operation state, and it has one function. This slide right here, this is the heart and soul of the sender-receiver model of P2300. These four concepts together, you can use to express any asynchronous computation. Okay. Let's go under the hood and look at what happens when a composite concurrent operation executes. And let's go back to our when all example. So you might remember this slide. Here's our code, and here is an illustration of that tree that it builds. And so we know that all of these things, these boxes, are senders. Since they're all senders, we know that they all implement this connect function. Okay. So what happens when we connect this with a receiver? Well, the sender is going to enrich the receiver. It's going to wrap that receiver in another receiver. And that receiver is going to have some of the logic of that algorithm in it. And then it passes that thing on to its child operations. In this case, there's 3 of them, so it's going to build 3 of these receivers. Passes it on. Those receivers wrap a receiver around that. And that passes it on to this innermost operation, right? And it doesn't have any child operations, so what it does with the receiver is it builds an operation state. And it returns the operation state to its caller, which is going to add another operation state and another. And this is going to be the operation state representing that particular asynchronous computation. So here I'm using solid colors to represent receivers. I'm using these hashed colors to represent the operation states. And since we know this is an operation state, we know it has a start function on it. So what happens when start is called? Well, start is going to recurse into the children. The operations execute outside in. Okay. Now, if you remember, this purple circle here in the onion, that is the schedule operation. Okay. So when start is called on that particular operation, what it's going to do is it's going to schedule the work on the thread pool. It enqueues it. All right, now time is going to pass, and then eventually a thread in the thread pool is going to pick that work up and execute it. And it does that, it completes, that schedule operation completes by notifying the receiver. So we know that these things are receivers, so they have these 3 functions, set value, set error, and set done. And so if this work has been scheduled and is now going to be running successfully, it'll probably be calling set value. So set value runs, and it recurses into its children. And eventually this innermost one is notified that the work is complete. Okay. Now, if you recall, everything in blue here was added by the when all algorithm. Everything in pink was added by then, and this purple circle was added by schedule. And I should point out that these are layers of behavior. They're not necessarily layers of data. The resulting operation state may actually be quite small, despite having many, many, many layers. So don't worry about like, oh my God, this operation state is going to be this enormous thing. It's not. So you'll notice that every adapter here, and by adapter I mean like when all and then, has a chance to run code when the operation is starting and when the operation is finishing. So it gets to bookend every asynchronous operation, and in this way, it can implement that algorithm's logic. Okay. This might remind you of a couple of different things. It reminds me of Russian nesting dolls. So senders nest, receivers nest, and operation states also nest. That's what's happening under the covers. All right. Let's look at a really simple example. let's implement a simple version of the then algorithm from P2300. Here, really simply, is the then algorithm. Let's see. Okay, here's a then algorithm. It takes a sender and a function to chain onto the completion of that sender. It returns a sender, and all it does is it curries all of the arguments into some larger object. Okay. And here's what the then sender looks like. It just stores that input sender and function, and we know it's a sender, so it has to implement connect. So connect accepts a receiver, and what it does is it wraps that receiver in its own receiver to add its own behavior. And you'll notice in this case, it just returns the inner operation state directly. It doesn't actually need to specify any work to happen when this operation is started. So it can just return the nested operation state. Okay. And here's then receiver. So it's a receiver, so we know it has to implement set value, set error, and set done. Here is where the interesting thing happens. Here's where the logic of the then algorithm is placed. So when this then receiver is called, after the input sender has completed and yielded its values, rather than forwarding those values on, what we do is we send those values through this function, f, that the user gave us. And in this way, we have chained that action onto the asynchronous completion of the input sender. And whatever this function returns then becomes the new value that we pass on to our inner receiver. I should point out, if this function happens to return void, that this isn't going to compile. So you'd need like an extra overload to handle the void return case. Set error and set done, they're not that interesting. They just pass through to the inner receiver. So that's what this looks like. You have set error that just passes the error through to the inner receiver, and set done that just passes the signal through to the inner receiver. Okay. So this is the entire implementation of totally workable then algorithm. The one in P2300 is a little bit more complicated because standard library implementations have to handle lots of details. But this works. Okay. And this is, if you were the sort of person who is interested in writing generic algorithms, this is sort of the code that you would be writing. All right. I'm really keen to talk about senders and coroutines. I know a lot of people are very interested in the topic of coroutines. Well, I want to point out that all awaitable types, in this case, you'll see we got this function, which is maybe reading a socket, returns a task. Task is like a coroutine type. We can pass that task to the sync-wait function, which is expecting a sender. And I should also point out that this task type doesn't actually need to know anything about sender-receiver. It just needs to implement the awaitable interface. Things that are awaitable, you can co-await. Things that are awaitable, you can co-await, obviously. You could also pass them to senders, and you can connect them to receivers. And that information, that logic is baked into the sender-receiver customization points. They just recognize awaitables and treat them as receivers by adapting them. And no extra allocation of synchronization is required to do that adaptation. I mean, of course, it's an awaitable, so you'll need to spin up a coroutine to await it, but you were going to do that anyway. So no additional allocation or synchronization is required. Now, the opposite is true also. You can co-await a sender in a coroutine. So here we have these two functions, two concurrent reads of sockets. They're executed by the when-all algorithm. And we know that when-all accepts senders and returns senders. So when-all is returning a sender here, but it's being co-awaited, which is fine. Because this particular task type here from the Unifex library is aware of senders. And it knows what to do when you co-await a sender. And P2300 makes it very easy to author coroutine types that are aware of senders. Well, as easy as authoring any coroutine type ever is, which is generally not easy. But this part of it, making it aware of senders, is actually fairly simple. And by the way, no extra allocation of synchronization is necessary here to do this adaptation. This is what P2300 offers the authors of coroutine types like task. If you've never played around with coroutines, this might not mean a lot to you, but every coroutine type needs to have a promise type within it. And if you want to recognize senders as awaitable within that coroutine, what you do is you inherit from this thing called with awaitable senders. That's it. You get all the goodies associated with that, making your senders awaitable. All right, now, if you're really sharp and paying attention, at this point, you might have a question. The question is, what happens? Let me back up here. Okay, so you're co-awaiting this sender. This sender could complete in 3 different ways. It can complete with value or an error, or with cancellation. Now, value is simple, right? It just returns the values, and we get access to them. Great. Error, that's also fairly straightforward. Coroutines support exceptions. That could get thrown as an exception. Cancellation, though. What happens when a sender completes with cancellation within a coroutine? Because coroutines don't have a channel for cancellation, which is unfortunate. So if an awaited sender completes by calling set done, it behaves as though an uncatchable exception, and I put exception in scare quotes here, it's not really an exception, but it behaves as though an uncatchable exception has been thrown. In other words, maybe this coroutine was started by another coroutine, which was started by another coroutine, and so on, like in some asynchronous call stack of coroutines. That entire stack of awaiting coroutines is unwound, exactly as if an exception were propagating through it. Okay. And it's uncatchable in the sense that even a catch ... is not going to interrupt that exception's propagation. Exception. Okay. If you're familiar with coroutines under the hood, then you know that every coroutine has a coroutine frame that is at least notionally dynamically allocated. It might not actually be dynamically allocated, but you could think of it that way. And what's happening actually is that you have built a linked list of coroutine frames. That's what with awaitable senders gives you. And you walk that linked list and you delete each and every frame, which is going to cause local variables to be have their destructors run in exactly the same order as if an exception were propagating through it. Now, maybe you want to actually handle this exception. You don't want to completely unwind your entire asynchronous stack. And you could do that with one of these two algorithms that are in P2300. You can map that cancellation signal into either a value or an error, which is what a coroutine understands natively. And you can do that with done is optional, which would turn a done signal into a null opt. Or you could do it with done is error, which would turn the done signal into an exception of your choice. If the cancellation exception that's propagating through your asynchronous stack of coroutines reaches an awaitable sender boundary, remember these things adapt back and forth. So if what you're actually awaiting is not a coroutine but a sender, then obviously this exception can't propagate through it like that. You have no coroutine frame to delete. What happens is that that cancellation exception gets translated automatically back into a call of set done. So then you're back into sender receiver land. All right. And this allows the seamless propagation of cancellation notifications, even when senders and coroutines have been freely intermixed in your asynchronous stack. It's very convenient. Okay. So let's flash back to our example where we were transitioning execution context in a coroutine. I had mentioned at the time that what looked like an infinite loop is not actually an infinite loop. What I should say here is that the on, I want to say on is like the start on function. So what on means is it's going to start execution on this context. I should have said that earlier, apologies. So this is not actually an infinite loop because we know that awaiting these senders might actually exit with cancellation. And if it does, then you're going to immediately stop executing this coroutine and propagate the exception to your caller. So in that way, you can ask this infinite loop to please stop, and it will. Okay. Okay. Now, if we look at executing concurrent work, here we're doing it with senders composing other senders natively. And maybe you don't like this particular syntax. Maybe you like working with coroutines. Cool. I can create a local coroutine with a lambda that schedules that work onto that thread pool and then completes. And I can co-await that. And then I co-return compute intensive. And then I can call this compute lambda 3 different times with 3 different arguments, send those 3 tasks, now coroutine tasks, coroutine tasks to the when all algorithm, and then co-await and then sync wait the result of that. Okay, so you don't have to work with senders. You can work with coroutines if you want. Okay. So the point that I really want to make here is that if you are in the business of providing asynchronous APIs, what you really want to be doing is returning senders. If you return a sender, that asynchronous function, that asynchronous API, puts the choice of whether to use coroutines or not in the hands of the caller, which is where it belongs. The user of your API may want to use coroutines or may not. If you return a sender, you leave that choice wide open. That's all I really wanted to cover in this particular session. In the next session, we're going to be talking about structured concurrency. We'll talk about cancellation support, like how it's actually implemented under the covers. And we're going to work through a really extended example of senders, receivers, and of course ranges. Because if you know me, I'm a fan of ranges. All right. So if you're interested in reading the execution paper, STD execution, it's in P2300, and this is the link. This is where you can find it. And all of these ideas are implemented in libunifex. Libunifex is a project that I started with Kirk Shoup and Louis Baker back when we were working at Facebook. And it has been under active development for about 3-4 years now. It's used very heavily internally by Facebook, particularly in their mobile applications where they actually care about saving allocations and performance. And it's totally usable, but still experimental. Okay. So at this point, I'd like to take a look at the Q&A. Okay. And fortunately, this Q&A, I think this is pretty slick of Zoom. The highest rated questions get bubbled to the top. Okay. For the end somewhere, people talk about executors in the context of GPUs and other heterogeneous devices, but that requires to compile your callbacks differently. How's that supposed to work? That's a very good question. One that is obviously dear to my heart because I work at NVIDIA and care very much about GPUs now. And the answer is that the GPU execution context will be provided by a vendor like NVIDIA. And the you'll have to compile your code using an NVIDIA compiler. So it will compile your receivers using the NVIDIA compiler, and it'll generate the GPU code for you. Also, I should point out that all of these generic algorithms in P2300, they have default implementations, but they are also all customizable. So, for instance, eventually we'll be providing versions of the C++17 parallel algorithms that also accept schedulers. And if you pass a GPU scheduler to something like sort, you're going to want to pick a very, very different implementation of the sort algorithm for a GPU. So in that case, a vendor like NVIDIA would override the default implementation of the sort asynchronous algorithm and provide a custom one for NVIDIA GPUs. So hopefully I've answered that question. Okay. Now, the $10 million question, how does debugging this look like? That's a great question. Debugging asynchrony is never easy. Never easy. And sender receiver inherently doesn't help with that. I don't think it particularly hurts with that. but it doesn't help. Generally, the state of the art in asynchronous programming is either fire and forget work on some execution context, or it's promises and futures, either using the standard library or a library like Boost or something. And then you're expressing your asynchrony with raw callbacks, chaining operations with .then, the future .then, and debugging that is extremely painful. But in the next hour, I'm going to be talking about structured concurrency, and I'm going to be talking about what that is and why it's important. And I'll give you a preview. Coroutines are structured concurrency. So in structured concurrency, you have parent operations whose lifetimes, whose activations nest, extend past that of their children. So in that sense, it's exactly like ordinary synchronous function calls, calling a coroutine. And so you end up with an asynchronous stack, just like a regular call stack. It's not, if you stop in the debugger in a coroutine and you examine the actual runtime call stack, it's not going to look very interesting. You're not going to see how you got there, the chain of activations of coroutines. But eventually, debuggers are going to become hip to this, and they're going to be acquiring the ability to walk coroutine frame chains and present to you the asynchronous call stack. Now, there's people working on it already. And if you can view the asynchronous call stack in a debugger, well, the advantage for debugging is obviously huge. Because then you'd be able to know, at this point in my program, you'll know what's executing, of course, but you'll also know why. How did you get there? Who's waiting for this operation to complete? Who started it? It's all right there in your asynchronous call stack. So although sender-receiver doesn't actually do anything particularly to help with debugging, structured concurrency most definitely does, particularly coroutines. But sender-receiver is also structured concurrency. Okay. Hope I've answered that. So slide 39, it looks like your C-style casting to an R-value reference. Is that a new revised idiom I missed, or just a quirk for the sake of brevity? Ah, yeah, okay. 39. Yeah, 39. So this is something that I do. It's probably not good practice. I don't recommend it. It's pretty handy for slideware to use C-style cast to do your forwarding of R-value references. Sorry, I should say forwarding of universal references. I said don't do what I do, but it makes it fit on a slide, which is one nice thing. Mentally you can replace this with stood forward capital R of R underscore. Or actually, this is in this particular case, this is a move. So you could replace this with a stood move, and you could replace these with stood forward. Now, I don't recommend this style. Sorry. Okay. Oh, good question. Executors in the standard when? Okay. So this is something that has actually been settled recently. or not exactly settled. But the committee has picked a direction and a goal to shoot for. So we are trying to get P2300 done and in the bag for C++23. That's the hope. We have a lot of work to do. We might end up missing that, in which case it would be 26. But if that were to happen, you could expect to see P2300 landing in the working draft immediately after C++23 ships. But I'm keeping my fingers crossed for C++23. Okay. How is heterogeneous computing addressed with this proposal? And if it is, do CPUs like M1 with an SoC and unified memory architecture throw a wrench in the mix? No, actually, CPUs with a unified memory architecture sit very nicely in this model, because you don't have to compile code well, you do have to compile it with a special compiler, but you don't have to annotate your code with, this is a host function, this is a device function, or anything like that. So generic code that is not written for device, can be compiled for device, and the right thing happens. Now, you might not get the most ideal performance that way. Sometimes, this doesn't entirely obviate the need, if you're a real speed freak, for dropping down to, say, raw CUDA if you're a GPU programmer. But we should be able to get 90 to 95% of the performance by giving people these generic standard algorithms to use. And the idea is to lower the bar to entry for people interested in accelerating their applications. They could just write portable C++ standard code. Pick an executor from a vendor like NVIDIA and have their code accelerated. That's the hope. That's the goal of this proposal. And how is heterogeneous computing addressed? Well, I feel like I addressed that already. Like, it's addressed by making the system open and extensible for a vendor like NVIDIA to provide custom backends to accelerate things. Distributed computation as well. Yes, absolutely. Since distributed computation is inherently asynchronous, I think it's a very good fit for sender-receiver and asynchrony. The idea is, if you have, say, a cluster of GPUs, both, some GPUs within your machine and some scattered across the network, the idea is that you should be able to abstract all that away and have a runtime that dispatches the code to the correct location and returns the results asynchronously. And all of that is implementation details of some algorithm. Seems the networking TS has been waiting on schedulers for quite some time. Will this proposal free it to be finally part of the standard? The work on the networking TS and the work on executors has been decoupled. So those two things can now progress independently. So in that case, the networking TS is no longer waiting for this work. It has its own model of execution. The committee would really like to see all of that unified. That hasn't happened yet. That's work yet to be done. We are moving forward with P2300 for C++23. It's a much smaller chunk of work, so it's something that we can bite off realistically. Networking is something that is still being actively worked on. Does this replace using the futures and promises already in the standard? What happens with those? Well, this is a great question. I'm glad this question was asked. So you might wonder, with sender receiver, do I need to build my entire asynchronous application as one gigantic tree of lazy work, and then async wait that whole thing in main? And the answer is no, you don't. And you don't have to wait until the very end in order to begin executing. So it's very easy to write an algorithm, a generic algorithm called as future, that accepts a sender and returns a future, that launches that work and returns the future as a handle to that work that's currently running. That could actually be a very useful thing. Now, we thought about actually proposing that algorithm for P2300. We decided against it because, well, frankly, we think the standard future type is fairly broken. And we don't really encourage a whole lot of people to continue using it. But if you're using something with, like a boost future that allows continuations, then it might be a very useful thing to be able to convert a sender into a boost future. So no, this is intended to be a lower level strata on which higher level asynchronous functionality can be built. So things like futures, things like channels, things like message passing, things like even reactive streams. All of those things can be expressed efficiently using sender receiver as the primitive abstraction. And in fact, we expect that people will be doing that. To be honest, I expect most people will be dealing primarily with coroutines and those higher level abstractions, and not so much with sender receiver. Just as with, if you're using the range algorithms in C++20, range is a nice high level abstraction. Under the covers, there's iterators. It's all iterators down at the bottom. So that is your fundamental abstraction. Range is a higher level abstraction built on top. And I expect the same will happen with sender receiver. How does this work with STD-EXECUTION, or does it not intersect? Well, that's a good question. We're hoping that in the end, when our work is done, we'll have actually made STD-EXECUTION useful, because it's not currently terribly useful, I don't think. It would be very nice if there was an overload of async that took a scheduler, and then we could specify like where this work should happen. So I think that's a promising direction. That's not our focus right now, though. We're just trying to get the basic building blocks in place. Is the executors proposal currently targeting the C++23 standard? I've answered that one. Yes, absolutely. Folly also has executors. How are the Folly executors different from the C++ standard ones? That's a good question also. Folly's executors are a lot like the executors in the networking TS, which are a lot like the executors in Boost ASIO. And they are a fire and forget model of programming. So they have a function called execute. They take a function and they just execute that function on that execution context. And done. Which is a simple model, but it's actually, and I'll talk about this in the next part 2. That actually has some complications for software composability. So this is actually intended to be a model of that is composable, that'll supersede things like Folly executors. Looks like I am being asked to wrap up now, so I think I'm not going to be able to answer any more questions. If you have a question I didn't get around to it, my apologies. You can find me after part 2 in GatherTown and ask me your question then. I'm glad I saved a lot of time for questions at the end. There was lots of good ones. Come back for the next session, please, part 2. We'll get to look at more code. All right, thank you very much.